Okay, so now we're going to talk about what is called the Nernst equation. And now my question is, well, what if the concentrations aren't actually 1 molar? What if we're not at the knot, right? What if we're not 1 molar, 25 degrees Celsius, and 1 atmosphere? What happens then? Okay, so then it would be, we're just E, not E naught, okay? We're not at standard conditions anymore. And if you think about it, what happens to a battery over time is the voltage is going to go down and down and down until it dies, because the concentration of those chemicals doing that reaction actually changes, okay? So what is the equation that relates those? That is the Nernst equation. So this is the Nernst equation, E cell equals E naught cell, which we can calculate with our voltages, minus 0.0592 over N log base 10 of Q. Again, your number of moles of electrons being moved. We can calculate Q just like we calculate K with our new concentration. So I've got, what would you expect to happen if I have a copper at a 0.1 molar and zinc at 0.1? Okay, so I changed the concentrations. They're not both at 1 molar anymore. Okay, well, if I look at this equation, all right, E naught cell, I can calculate with copper and zinc. If I pull that from the list, I do 0.0592 over however many electrons are being transferred. And well, I've got Cu plus 2 and zinc plus 2, so it must just be 2 electrons that are being transferred. And then log Q. Now to figure out what Q is, you have to actually write out the reaction. Okay, so I did that first. I wrote out this reaction. I've got copper 2 plus zinc makes zinc 2 plus copper. Now, why did I write it this way? Okay, I'm going to pull up the sheet to show. Okay, so I have copper and zinc, right? So remember, whichever one is higher is going to go in the forward direction. So I've got copper right here, and I have zinc down here. So that means copper is going to go forward, so it is going to be reduced, and zinc is going to go backward, zinc is going to be oxidized. So all I did was put those into the same equation. Okay, copper is going to be reduced from +2 to regular, and then zinc is the one that's going to be oxidized from zinc to +2. Now you do have to make sure this is balanced charge-wise. Okay, so this is because I got +2 on one side and +2 on the other side. There's only 2 electrons being transferred. We are all good. So if this is the equation, I want you to notice that I wrote aqueous with the ones that are charged, because those are in solution, and solid with the ones that are solid, like the metals, okay? So if I were to write the Q equation or the K equation for this, it would just be zinc 2 plus aqueous over copper 2 plus aqueous, as I have written here. Why? Because solids are not included in the K equation or the Q equation. So it's just zinc concentration over copper concentration, okay? Now, if they are the same concentration, then Q is just 1. Okay, so if that's true, like if they were both 1, which would still be standard, log of Q, if it's 1, the log of 1 is just 0. So this whole thing goes away, and then it says E cell equals E naught cell. So technically, if they're at the same concentration, it's not going to change my voltage. And yes, that is true. It's not going to change the voltage. It's just not going to last as long as if you had 1 molar and 1 mole. Okay, so same voltage, but the same concentrations are just going to make it not last as long, essentially. Now, often we just don't have the same concentrations. Okay, so then we are going to actually use the Nernst equation. This was just to kind of show you what changing Q values actually does to this equation mathematically. Okay, so if I said calculate the cell electromotive force for the non-standard conditions. So if it's for non-standard conditions and I'm looking for that E cell, I need to use the Nernst equation because this is non-standard. It doesn't have the little knot. Okay, so I wrote that down here. I first had to find my E naught. Okay, so I pulled my reactions from my table. Same thing I did up here, copper and zinc. I wrote out my equation to make sure I had a balance so I knew how many electrons were being transferred. That's going to be important. And I did cathode minus the anode. So the cathode being the one that is reduced. So what is that? Copper minus the one that is oxidized is zinc. So I get 1.10. So my E naught for this reaction is 1.10. Now, the problem is they're not both at 1 molar, right? I have this concentration and I have this concentration. So I use the rest of the Nernst equation minus 0.0592 over 2, because in my balanced equation, I'm changing the charge by 2. And then the log of the zinc over the copper. Now, again, why did I do the zinc over the copper? Well, because of my balanced equation, zinc is my product and copper is my reactant. So write out the balanced equation to make sure you know what are your reactants and what are your products, okay? So the zinc concentration goes on top, copper concentration goes on bottom, and I calculate that the value of this cell is actually higher than the E naught. It's 1.22 volts. Essentially, that's because since I have a higher concentration of copper, okay, yes, I have a higher concentration of copper in this instance. So that means it's going to go to the right to balance out, kind of like Le Chatelier's principle. It's going to make more products. So it's going to be a more productive voltage. You can kind of think of it that way. Okay. So I think you should try B on your own. Go ahead and pause it here. Okay, and I'm going to walk through this. So again, I have my equation written here. Now I can either check my potentials to see which one is the cathode and which one is the anode, or remember, this is always written anode and then cathode. It's always written in the way that it's going to react. So zinc is going to turn to zinc plus 2. So you'll notice my equation over here, I wrote zinc as a reactant and zinc plus 2 as product. And then silver is going to go from Ag plus to Ag. So I've got Ag plus as a reactant, Ag over here. Now that balancing charges wise is not balanced. Okay, because I had a +1 over here and a +2 over here. So I actually need 2 silver. So I have a +2 charge over here, and then I needed 2 over here as well to make sure that that's balanced. So now I have 2 electrons being transferred. Okay, so make sure you balance that. Now, if you're not sure how to do that, go back to the balancing of redox reactions. It's just, you can leave out a whole bunch of steps because we don't need water and stuff in these. Okay, just make sure your electrons are balanced. So then I calculated my E naught cell for this. Okay, whichever one was being reduced, so cathode minus anode, so the one being reduced is silver, so 0.80 minus negative 0.76, I get 1.56 volts. Oh, sorry, the one being reduced, yeah, was silver. Okay, so I get 1.56 volts for my E naught. Okay, so I have my E naught cell, so that goes here, minus 0.0592 over 2 electrons, because I'm transferring 2 electrons, and the log of the zinc concentration over the silver concentration squared, right? Because if I were to write out the K or the Q equation for this, it would be product, so just zinc, over, since this has a coefficient of 2, it does have to be silver squared. So please write out the equation, otherwise you're gonna forget that that's squared, all right? So I plug those in, and I get 1.42 electron volts. Okay, try again, one more time. For C, it's just a more complicated balancing. Make sure you balance the equation. Okay, so this is my balanced equation. I actually have 6 electrons being transferred. So the value down here was 6. It's magnesium cubed over indium squared. So you do have to use those values when you're calculating. You should get 1.94 volts.